Hello, my name is Dr. Gerard Hobley. There are 3 videos covering AS level chemistry energetics. This is video number 2. This video lesson is about answering exam questions involving Hess's law. Let's just recap briefly what was covered in the last video. We defined Hess's law as, irrespective of the route taken, the overall enthalpy change for a chemical conversion is the same. We looked at some important definitions and conventions which we need to know in order to correctly work out thermodynamic quantities from other data. We defined the meaning of the terms delta H formation standard and delta H combustion standard, and we learned what the term standard conditions refers to. We also looked briefly at how to draw equations for the processes that we are given thermodynamic values for, and how it was vitally important to specify the state of the material that we are discussing, either gas, liquid or solid. And we learnt that delta H for a reaction equals the sum of delta H formation for the products minus the sum of delta H formation for reactants. Now let's apply this knowledge and solve some problems. I'm going to show you 2 ways of doing the same sum. In the AQA A-level specification, it says students could be asked to find delta H for a reaction using Hess's law and calorimetry, then present data in appropriate ways. Examples of reactions could include the thermal decomposition of sodium hydrogen carbonate. So let's look more closely at the thermal decomposition of sodium hydrogen carbonate as an example. The chemical equation for this reaction is 2 NaHCO3 solid, and heat it to 100 degrees C, goes to sodium carbonate solid plus carbon dioxide gas plus H2O gas. I'll make that O a little bit more oxygen-like. H2O gas. So we're going to use the equation that we looked at last week. Delta H for the reaction equals the sum of delta H formation standard for the products minus sum of delta H formation standard for the reactants. Quickly going to change this colour. So that's a nice pink. So look, I'm going to look up the delta H formation values, standard values for these 3 things. I'm going to enter these, add them all together, and enter them into this part here. And then I'm going to do the same thing for here. I'm going to enter it into this part of the equation here. Then I'm just going to do this sum. So we can look up the delta H formation standard values for the reactants and the products and then calculate delta HR. I'm going to add that I'm using 2 moles of reactant, sodium hydrogen carbonate. So any value obtained will be 2 times the standard enthalpy of this reaction process. To look up the data, up the thermodynamic values, I'm using the Nuffield Advanced Science Data Book, copyright 1972, 1984, the Nuffield and Chelsea Curriculum Trust, which is freely available online at at the web address https://www.stem.org.uk. This book is used throughout this 3-video series. So I've been away and I've looked at the values. The equation is on the top here. 2Na8CO3 solid goes to Na2CO3 solid plus H2O liquid plus CO2 gas. Now some of you will notice that what I've done is change this from H2O gas to H2O liquid. That's so that if you go away to the internet and look up the value, then you're more likely to find an answer to the sum corresponds to the sum if it's worked out with H2O liquid, and that will save you from basically panicking and believing that the method is wrong, which it isn't. The method is right. So I'm going to enter the information in a table. So I'm going to quickly draw a table here. And in this line we have this column substance, this column delta H standard in kilojoules mole. So we'll start off, we'll put H2O liquid, and the value is minus 286. CO2 gas, the value is minus 393 kilojoules per mole. Na2CO3 sodium carbonate solid is minus 1131 kilojoules per mole, and sodium hydrogen carbonate solid, the value is minus 950 kilojoules per mole. So we need to plug these values into the sum that we're using for delta HR. Sum of delta H standard for the products minus sum of delta H formation standard for the reactants. And let's put these values in. This is minus 1131. It's the sum of, so we're going to add. So the 1131 is for sodium carbonate, which is one of the products. That's carbon dioxide minus 93 plus water minus 286, and that's the products dealt with. So let's add the reactants minus, and we have two equivalents of sodium hydrogen carbonate. So we're going to put a 2 here minus 950. So we could just either plug all of that into a calculator, or we could simplify it first. So we'll get rid of the brackets. Minus 1131 minus 393. Let's get rid of that. Minus 286. This all comes out to plus 1900. And the answer is 90 kilojoules. So if we need that in terms of kilojoules per mole, we need to divide it by 2. So 90 divided by 2 equals 45. And the 2 here comes from all the way over here. Yeah. So the sum is for 90. 90 is for 2 moles of that, so it must be 45 for the 1 mole. Per mole. So we were given all of the information. All we needed to do was to organise this into a form to do a relatively simple sum. We can organise this information much more graphically, and this can be quite useful. So let's have a look at that next. So let's start again. 2 NaHCO3 solid goes to Na2CO3 solid plus CO2 gas plus H2O liquid. What I'm going to do now is draw 2 lines representing chemical potential energy levels here and here. So it's chemical potential energy levels. What I'm going to do is move these down to the bottom and then draw another line up near the top, a new chemical potential energy level here. And if we remember, delta H of formation standard is the energy change when 1 mole of substance is formed under standard conditions from its elements standard form. So I'm going to enter the elements new level in their standard form. 2 Na solid plus 2 C solid plus H2 gas plus 3 O2 gas. Now, the contents of this box can be mixed together and used to make the contents this box. So there's two sodiums, two hydrogens, two carbons, and 2 times 3, which is 6 oxygens, which is exactly the same here. And it's also exactly equivalent to this box here. So what I need to do is to start to enter the energy changes then. So delta H of formation of sodium hydrogen carbonate is 950, and we're making 2 moles of that, 2 equivalents. So let's say this is 2 minus 950 or minus 1900. Then to make sodium carbonate, value is minus. To make carbon dioxide, value is minus 393. And finally, to make water, value is minus 286. And I'm going to call this one X. So this line plus this line equals this line plus this line plus this line. So let's enter that up here. Minus 1900 plus X equals minus 1131 plus minus, which is a minus 3 minus 286. So therefore X equals minus 1131 minus 393 minus 286 plus 1900, because what I'm doing is adding 1900 to both sides. And if I do that sum, then the answer comes to 20 kilojoules. Because I've got 2 equivalents here, remember, or 45 kilojoules per mole. Now that's quite simple. However, some people might not get that straight away. So I'm going to show you another way of looking at it. I'm going to rub all of these out. And what I'm going to do is I'm going to redraw the whole thing, but as a cycle. So I'm going to make all the arrows go clockwise. If I have to reverse an arrow, I need to change the sign value of the energy change. So for this one, which was minus 1900, I'm going to draw it this way round, so it's going clockwise. It then becomes 1900. This one here was X. I'm going to change that to minus. And then these arrows are exactly the same as they were before. Just draw these in quickly. -1131, -393, -286. If I think about it, if I go all from this chemical potential energy level all the way around the cycle back to the same energy level, and the overall change in chemical potential energy must equal 0. So if I give these a label, each one of these a label, I'm going to label it as A equals 1900, B equals -1131, C equals -393, D equals -286, and E equals -x. I can now say A plus B plus C plus D plus E equals 0. So I'm going to subtract E from both sides. A plus B plus C plus D equals minus E. Since E equals minus x, x equals minus E. So I can therefore say x equals A plus C plus D. And what I'm going to do is put these numbers in. Let's make some room here. So x equals A plus B plus C plus D, which equals 1900. That's going to be minus 1131 minus 393 minus 286. If I add all of that together, then the answer is, as we expect, 90 kilojoules or 45 kilojoules per mole. And I'm going to just make sure that I'm specifying that that is for the NaHCO3. And that should be a solid as well. Solid. Put those into square brackets. So if I think about this now, I could take any value, any of these values, and work them out from all of the other values, because it's a complete cycle. So let's just prove that. Let's get rid of a lot of this stuff. We don't need to get rid of everything. Let's leave some of it. So we're going to call this value just x. This value is 1900 and E equals minus 90. If it's going this way, it's 90. So x is 90, but going this way, this direction, it's minus 90. So using the same logic as before, a plus x plus c plus d plus e equals 0. Therefore, a plus c plus d plus e equals minus x. Let's put numbers in. 1900 plus minus 393 plus minus 286 plus minus 90 equals minus x. So I'm just going to do that sum on my calculator. So minus x equals 1131. Therefore, x equals minus 1131 kilojoules per mole, because I'm making 1 mole of sodium hydrogen carbonate, and it's the delta H of formation of sodium hydrogen carbonate. So we've looked at solving thermochemical problems using values for delta HF standard. I've shown you 2 different ways of organising the information given. That will help you to solve the problems. If you find that you struggle with these kind of problems, then you need to practice them. There is a lot to remember, and falling down on some small detail is a very common problem. Remember, practice makes perfect. In the next video, we will look at average bond energies and delta H combustion standard values to solve similar problems. Please visit our website https://xscience.wordpress.com. There's a link below this film where you can gain access to videos and associated PowerPoint slides, worksheets and answers, tutorials, in-person tutorials for people living in the United Kingdom, other chemical education resources, a range of educational chemistry videos covering topics which students find most challenging. Those things marked with an asterisk, we will post them as we develop them. Thank you very much for your time.